is a question that I'd like us to keep in mind as we go through the contents of this video. When we use the terms machine learning, deep learning, and representation learning, what exactly does learning mean? Learning a function is the same as reverse engineering a function. So, when a system or an algorithm learns a function, it knows how to reverse engineer or how to go from the input to the output without having access to the underlying code. True or false? We now have a decent sense of TensorFlow's mechanics of how programs are set up and implemented on TensorFlow. Let's turn our attention back to the neural network and to its most basic building block, the neuron. Let's now understand the role that neurons play as learning units. The neural network based classifier that we are using to classify a corpus of images and to see whether they are images of fish or mammals is, in a sense, learning a function. This is a function which tells us how those images link to their output label. And that function is learned using these layers in the neural network. This is what the feature selection and classification algorithm is all about. Some layers in that neural network are learning what the pixels represent. Other layers are learning what other features of the image represent, edges, contours, and so on. But the intent of all of these layers in the neural network is the same. It is to learn or to reverse engineer the relationship between the output and the input. We shall see in just a little bit how this reverse engineering is carried out using the interconnections between individual neurons. Let's now be clear in our head on what the learning process is all about. A machine learning algorithm is one that is able to learn from data. This is a pretty standard definition of machine learning. The question that now arises is, what exactly is learning? How do we quantify this term? How do we tell whether an algorithm is actually learning from data or not? This brings us to the definition of learning algorithms. A famous textbook has defined learning algorithms like this. We will parse this definition in a moment, but the bottom line of this definition is that a learning algorithm learns or improves with experience. It reverse engineers the output and it improves the quality of that reverse engineering by taking advantage of the training data. So let's parse this. The first bit in this definition is the term tasks. Now, there are a bunch of standard tasks in machine learning: classification, regression, clustering, and rule detection. We have already had some exposure to three of these: classification and regression, as well as clustering via the k nearest neighbors algorithm. Now, clearly, in order to tell whether an algorithm is getting better or not, we also need a performance measure, and performance measures are specific to the individual tasks. So, in classification, it might be the accuracy; in regression, it might be the residual variance, or it might be a metric known as cross entropy if you're using logistic rather than linear regression. All of these are performance measures which tell us how well our learning algorithm is improving. Much like human experts, a learning algorithm improves with experience, and that experience is in terms of the training process. It's in terms of exposure to a number of labeled instances, that is a corpus. So, putting all of this together, a learning algorithm learns from experience, which means that it improves its performance at tasks as measured by some performance measure P. This is the heart of a learning algorithm, and this really has to do with tweaking the insides of a model during the training process. It's relatively straightforward to understand how an algorithm like linear regression learns. Given a large number of data points, these constitute its experience, it will tweak the values of its constants. Those are the slope and the intersect of the regression line, and it will tweak these in ways which decrease the loss function, i.e., increase the performance. This process of learning is easy to quantify and understand for simple algorithms, but it can be a little challenging to understand how deep learning algorithms actually learn. In a nutshell, deep learning algorithms learn by tweaking the variables which are the weights of their neurons. We'll have more to say on this using a couple of examples. The simplest possible example, which is regression using a single neuron, and then a slightly more involved example involving XOR. Learning the XOR function requires three neurons arranged in two layers. We shall see how such a neural network can learn the XOR function via a training process. Before we plunge into that, let's once again reiterate the exact relationship between neurons and neural networks. Layers in a computation graph represent groups of neurons which perform similar functions. Each layer is going to consist of neurons which are then interconnected with neurons in other layers in possibly very complex ways. And as we've discussed, the term deep learning arises because there are many layers of neurons arranged in depth. The directed computation graphs, which we discussed in the context of TensorFlow, learn the relationships between the data. The more complex the graph, the more the relationships that it can learn. For instance, simple functions such as linear regression can be learned using a really simple graph. Just one layer, that's one neuron, will suffice. As we shall see, to learn an even slightly more complex function such as the XOR function, we will need two layers and three neurons. Clearly, we can learn more and more complex functions by adding more and more layers and more neurons connected in increasingly complex ways. The interconnections between these neurons and how they learn that complex function very quickly becomes opaque to us. Very quickly, neural networks become black boxes, but that doesn't really matter. As long as they learn a complex function, that's really all that we care about. And again, the term deep learning refers to the fact that to learn a very complex function, we are going to stack many layers one after the other. So, for instance, to learn a linear relationship between a y and an x variable, one straight line is enough. This is the whole point of linear regression. And to learn a linear regression, all that we need is one single neuron. A single neuron is enough to reverse engineer linear regression. And here is how this would play out. We would start as usual with a set of data points. These would then be fed into the simplest possible neural network, which just consists of one neuron. That neuron would then undergo a training process in which it would tweak or optimize its own parameters based on that training data, and it would then output a regression line. And as we shall see, the reason that regression can be learned using a single neuron is that one neuron performs two operations, and one of those operations is a lot like linear regression. It is an affine transformation of the input. But now let's say that we wish to learn a non-linear function like the XOR function. Here, what we really need to do is to reverse engineer a function which can be represented in pseudocode as above. This function has two inputs, x1 and x2. If the values of x1 and x2 are equal to each other, we shall return 0, else return 1. And as an aside here, let's just assume that x1 and x2 are both binary variables, they are bits, so they can only be 0 or 1. This is a non-linear function, as we shall see, and so reverse engineering this requires a more complicated function consisting of three neurons arranged in two layers. Training such a network is already much more complex than training a single neuron, and so this is a training process which we will not really understand. The training will be handled for us behind the scenes by a framework like TensorFlow, but all that we know is that at the end of this process we will have three neurons which accept a pair of inputs. Those neurons will have certain specific weights and biases, more on these in a moment, and the net effect of all of this will be that our neurons will be successfully able to reverse engineer an XOR function. This means that if we pass in different values of x1 and x2, the outputs will exactly match that of the XOR truth table. And we shall see how this training process plays out in more detail. Extending this analogy, it is possible for neural networks to learn arbitrarily complex functions. If we could reverse engineer a bit of pseudocode which calculates XOR, by adding enough layers to a neural network, we can learn just about any piece of code. This characteristic makes neural networks extremely powerful and versatile. We may not understand what the resulting neural network exactly does or how it goes about reverse engineering the function, but we know that it works. This makes neural networks much more versatile than other methods. Consider, for example, a naive Bayes classifier. That is a very specific method which works brilliantly well for classifying data when we have probabilities available, but it's not going to be generalizable to use cases like classifying images. One last observation about a neural network, we can see that there are effectively processing units, these are the neurons, and data flows between those processing units. These are the data items or the tensors. This represents an exact correspondence, an exact parallelism with the computation graph in TensorFlow. And this parallel explains why TensorFlow is such a natural fit for building neural networks. Let's turn back to the question we posed at the start of this video, and this statement is actually true. Learning a function basically involves reverse engineering it. When we as human beings learn a function, something of the form y is equal to f of x, we learn what exactly the transformations on the x variables are during the course of that function. When a machine learning algorithm learns a function, it's doing exactly the same thing. It's going to try and match the output of the function without knowing or without having access to the exact code or the logic that went into the function in the first place. That satisfies the definition of reverse engineering, and that's why learning a function is indeed synonymous with reverse engineering a function.